Alright, dear guys, I'm here trying to just make additional video on the topic that we didn't cover for today's lecture because we had a few, let's say, around about 10 to 15 minutes dedicated to the extra activity on the teaching experts visiting. That's why we didn't finish our planned content for today, so I just have a few slides to just give you as a video. And we will start with the heat treatments as I just discussed with you together during the course. We covered mainly about annealing, actually not all of it. From the course today, annealing contains about stress relief annealing and spheroidizing and also process annealing and full annealing. So I will actually just pick up from full annealing because we didn't manage to explain it in detail and make a comparison between that with the quenching and tempering, and finally I'm going to cover the precipitation hardening for you to complete today's course. And just as we defined about the full annealing, it is a process looking exactly like that. So we're plotting this curve in the diagram of time versus temperature. So you know this diagram quite well already from the lecture last week. So we need to pay attention to those two solid lines and dashed lines. So probably remember the solid lines are indicating the phase transformation under the continuous cooling condition. So they're called continuous cooling transformation. And those dashed lines, they're referring to the isothermal phase transformation. So during a temperature just holding as a constant. Of course, when we're talking about the full annealing, it is a continuous cooling process, as you can see here. So we need to read the continuous cooling transformation curves. And by definition, full annealing itself is referring to a process. Firstly, you heat your material up to a full austenite regime. So here we're starting from the austenite phase, and we just cool it down very slowly. So probably the slowest that we could do in a furnace condition. So the furnace cools together with your materials. This is the slowest possibility you could have. And of course, you can imagine in the end, we will have, for our case here, a perlite phase and even a perlite phase with very coarse grains because the cooling rate is very slow and you won't be able to have too many nucleation sites, so therefore you're going to have rather large perlites. And just to make comparison, so you're already familiar with this process as we mentioned it several times. So we will have the quenching, so the rapid cooling, and you will directly get the temperature sensitive phase. So it is not too much related to a chemical composition, so it's just about temperature. If you have this, you're lower than this temperature and you avoid to have diffusion about to form any perlite or bainite, you will get your martensite. Yeah? So martensite is obtained through a diffusion-less transformation. So it is share-based. Yeah? So basically, the material is a single phase. It's a single BCT phase, as you still remember. But it is a phase which is not that in equilibrium, right? Because so probably some of you might ask why it's not BCC, it has to be BCT, because you need to recall our carbon has a certain amount of solubility in the alpha phase, right, in the BCC alpha ferrite phase, and it is not possible to have them just diffuse into a BCC phase. That's why when you just have your kind of oversaturated carbon in your iron matrix, you will not be able to have the BCC. It has to be BCT because the carbon, they want to go away and they couldn't. And that will just kind of create this kind of actual stresses, and that's why it is creating this BCT. So it is basically a consequence of the oversaturation of carbon, and it cannot go away from the iron, and it has to be dissolved into the iron matrix. That's why it also gave the chances for tempering. If you just gave a certain amount of temperature, and if you increase temperature above the martensite starting temperature, and the material will be not that stable anymore, because due to the very low diffusibility and room temperature, let's say, those saturated carbon, they're trapped in this BCT structure. They cannot go. But when the temperature is high enough and your diffusion is more active, so the carbon can easily try to go away, right? If you just have a look at about the tempered martensite microstructure, so this is what we get after tempering. You will see finally we will have a kind of rather a equilibrium phase. So we will have not the BCT anymore, you will have ferrite plus cementite. So all these small dots, they are referring to cementite. So these are formed just because the carbon which are saturated in the martensite, they really get the chance to leave this BCC martensite due to the solubility, and they can form finally to a stable cementite, which leaves also the martensite finally become ferrite, which is also stable. That is the mechanism for this tempering process. If you don't get it from last week or from the lecture in the morning, this will just give you a rather detailed explanation for this tempering process. Of course, you can even get more if you just try to read the book. And we have already spoken about the influence of tempered martensite on the tempering process to control the strength and also ductility. So basically, they're controlled by somewhat the size of this cementite. As you probably remember, it's always about size, and because it's finally related to dislocation, mobility, and that is always depending on not directly on the size, but indirectly, because it's depending on the boundaries, and the size is directly influencing the boundary. And you might also kind of see this microstructure is quite similar to the spheroidite microstructure. Yes, it is. And the only difference is about size, actually. So they kind of perlite, sorry, not perlite, they kind of cementite in the tempered martensite is much smaller than that is existing in the spheroidite. That's why the tempered martensite is still having a very high strength compared to perlite and spheroidite. Okay, so hopefully that gives you a more detailed explanation about tempered martensite. And let's move on to something more practical about quenching and tempering. I have to refer to the kind of case study I introduced in the morning. So if we are trying to get a kitchen knife with the quenching and tempering, that gives a really good combination for high strength and tolerable or balanced ductility or toughness. The question is, how do you control this kind of quenching how do you control the cooling rate so that you can for sure get martensite not really touching a little bit to the perlite or so. So that is something we need to discuss with respect to this cooling. So you probably just accept it as some numbers. So we have a cooling rate like 20 degrees C per second, but in reality, you have to achieve that somehow. Yeah, how do we achieve that? In industry, usually we use 3 methods, actually 4. You have learned already the first one, which is about the furnace cooling, right? This cooling of your material together with the furnace. That is not so much used except for full annealing, of course. But you can imagine that is rather slow. If we don't have specific requests, we would rather go to other conditions, especially for quenching. We would go really to find some fast quenching media. Here I'm giving you a list about 3 very common and inexpensive media. The first one is air. So basically you just get your material cooled down by in an open air condition. Actually, this is not really quenching. This is something will give you very low severity of quench, most likely even none. And of course, what you will have is very low hardness, right? Because you will not get too much martensite. Maybe you get some, but not too much. And the second media is oil, which already gives a rather fast cooling rate. So we call that moderate in terms of severity of quenching. And of course, you get rather moderate hardness as well. The fastest cooling rate is provided by water, actually. So you probably don't know, but if you just happen to have a chance to visit a steel industry, especially, you could have a look at their heat treatment process, and you will see water is used in many places. And that is used basically to cool down your sample because it provides the fastest cooling rate. You will have very high quenching severity, and it will also convert your material basically fully to martensite, and you will get very high hardness. So except for the quenching media, what is also important and you need to keep in mind, especially when you want to do a design work in the future in terms of product or material, what you have to think about is if the cooling rate is uniform. Of course it's not, right? So for our kitchen knife, that is rather a simple case because it's not a large volume, it's thin and it's small, so you can use water just to quench it rather fast and uniformly. But think about it, if you have a massive product, it is large, and especially the thickness is high. So that will mean the cooling rate will be not uniform. The center will definitely has less cooling rate than the surface, right? I mean, you don't have the knowledge about heat transfer yet, most likely, but I think from daily practice, you would be able to sense it, right? And that's why we need to always think about if you need to overcool your surface to make sure your center reaches a certain amount of cooling rate as you wished. This is a rather important issue to consider, especially when you design your product with a certain request on mechanical property. All right, that was for full annealing, quenching, and tempering. Here I'm introducing you the final heat treatment process in our course, which is called precipitation hardening. Actually, by the name, you can already see it is rather more a hardening mechanism than a heat treatment process. Yeah, in fact, the two elements of this heat treatment process are the two that you have more or less seen. So it is involving quenching and tempering. I will show you just in a minute. Because it is a rare process and it has a specific purpose, is to just produce precipitates and to just harden the material. That's why we are giving a specific name, which is called precipitation hardening, and we also call the kind of heat treatment procedures called as precipitation hardening procedures. So this is just some very basic introduction about this process. As we already explained, the purpose is to create precipitates. So precipitates basically is a name you can just imagine equal as very small particles. Yeah, and they are having the name as precipitates. And the purpose is basically to create those very small particles, or so-called precipitates, to kind of impede your dislocation motion. Yeah, because those small particles will basically kind of increase the obstacle density in your material, and that will decrease the dislocation mobility, therefore increase your strength. I think you're now very kind of fluent with this kind of logics already. And here we're looking at a aluminum copper system, so not about steel anymore. And by the way, this is also a hardening mechanism widely used for these light metals, not so much for steels actually. And let's just basically look at a phase diagram, because we didn't have a look at those kind of phase diagram for a while. And this is a typical, if you just recognize this, a typical eutectic binary phase diagram. We have aluminum and copper, and we have basically two solid solutions, either alpha, so with the aluminum as dominant element, or theta, when the copper is significant, actually still not too much dominated, rather in a balanced case. And these are the two solid solutions, and in between we have the mixture between alpha and theta. And how this precipitation hardening procedure is applied, as I just described you, it contains two steps. So the first step is basically to heat up your material to a alpha solid solution. Imagine we have such a chemical composition right here, and we will first heat it up to alpha, so you have completely alpha instead of alpha plus theta. And here then you're gonna give a process as quenching, as we show here. And this quenching, so different from steel, we will not have the transformation to martensite. Yeah, martensite is a special one for steel only. And for this aluminum copper system, you will not have martensite, but you will have a oversaturated alpha. Yeah, this is so because the cooling rate is so high, you don't allow any diffusion happening, which is triggering the alpha plus theta system as usual. Because you don't have enough time to diffuse, and your diffusibility of copper in aluminum at room temperature after quenching is so low, so the diffusion cannot happen at room temperature. That means this oversaturated solid solution basically is freezed. All the copper atoms are just trapped in this aluminum matrix. But as you can imagine, if we just apply a little bit of heat and you just reheat it into a certain higher temperature, here we're talking about a little bit about 400 degrees C, and the diffuse will be active again. And with this diffusion, you can easily see the oversaturated alpha will decompose to alpha plus theta, right? And those theta will basically just kind of nucleate inside of the alpha phase and become this very small particles, so-called precipitates. Yeah, and this is the whole process of precipitation hardening. As you can see, this is indeed very similar to what we have like quenching and tempering. Yeah, so for quenching tempering, we're usually just referring to this part. Yeah, we don't involve too much about this part. But you should be able to understand this is only a similarity in terms of how you play with the temperature, and the difference is significant. And the difference for the quenching and tempering, it is in the end to basically soften your material. But for the precipitation hardening is to harden your material. At least that's our goal. And I will show you how that is done. And just a few applications for not only aluminum, as you can see, this is widely applied to magnesium and also to copper even. And so after this precipitation hardening, what our material properties will become. So here I'm giving you a diagram for this 2000 series aluminum alloy. And the x-axis for this diagram is this precipitation heat treatment time. So this is basically referring to this kind of tempering time, but we don't call it tempering time just to avoid any confusion. So that's why it's called precipitation heat treatment time. So, and then we're plotting the y-axis as tensile strength, as you can see. This is something you don't do any heat treatment, and this is the non-equilibrium solid solution, of course. And if we just apply a little of time where you could have some diffusion, but the diffusion is not really significant, you don't have enough amount of your theta phase, and this will just cause a little bit of slight decrease actually from the initial case. I think you can also easily imagine what that happens. Yeah, because basically for the non-saturated solid solution, it's relatively hard because there's a lot of kind of internal stresses there. And if you just gave a little bit temperature, and the internal stresses will be somewhat released. And if you don't produce a kind of hard or large amount of the precipitates of the second phase, and you will basically have a drop of your tensile strength. But just soon after, very little amount of time is needed, you will dramatically increase your tensile strength by creating the small precipitates, which is the theta phase for our case. And the magnesium actually is a little bit more complicated than you probably imagine, because it's not just about creating a phase, and even not necessarily a hard phase. So this theta is not necessarily a very hard one. It can be even some cases soft. The main idea here is they should be small. It should be small enough to create all these boundaries, and they should be appropriate even to induce some distortion of your crystals. And all these two types of resources, either boundaries or the distortion of the crystals, they will just give rise to the strength, because the dislocation mobility will be hindered by two of them. And if you just kind of keep your precipitation hardening time too long, you will see the tensile strength will drop. Yeah. maybe you can also imagine what is the reason. The reason is because your kind of a small precipitate, they will just continue to do the diffusion, and they will kind of grow finally into somewhat larger theta phase, larger precipitates. And as you can imagine, the boundary is becoming less again, and your material is becoming softer. Yeah, so this is a specific phenomena related to the precipitate hardening. And due to this issue, because it's so sensitive to the time, we also call this precipitation hardening as aging. So as you just see here. So this is properly aged, and this is overaged. Yeah. So these two terms are just used to replace each other. So don't be surprised if you see I'm doing aging to my aluminum alloy. So now you know what they're doing, right? They're basically trying to make the material harder. And of course, accompanied by tensile strength, you also have certain reflection of the precipitation hardening on your ductility, and that is just the opposite, more or less, of your tensile strength, as you could imagine, with many kind of experiences already. All right, I think that is all for the content I would like to make up to you. And I think I spoke a little bit too long. Again, hopefully that will be not too problem for you. And oh, I'm even adding a extra slide to explain you a little bit problem that some of you asked, especially concerning the phase transformation, how to read this kind of temperature time diagram when we are trying to look at what kind of phase we will have in the end. So here I'm giving you a rather complicated issue actually. So here we're going back to the iron and carbon phase diagram again. So you see the most familiar curves that we say. This is the bainite perlite 100%. Here's bainite, and this is perlite 0, and this is exactly the change to produce from the liquid, from the austenite, I'm sorry. And then you also have the Martensite starting 50 and 90% of Martensite temperature. And we're giving with a specific chemical composition, 0.45 carbon. So this is, if you remember the phase diagram of carbon and iron, this is actually a hypoeutectoid composition. And I will just basically show you such a kind of temperature and timeline and explain to you why we're having in the end 50% of fine perlite plus 50% of bainite. And via this explanation, I'm trying to guide you how to read this type of curves. So basically here is showing you we're starting from completely austenite phase, and we're directly cooling down to a rather low temperature. So that means we will have a very high, if you remember, a very high cooling rate. Yeah. So what high cooling rate means? So high cooling rate means we're going to have a lot of nucleation points, right? So that is referring to we will have rather fine perlite. Yeah, that's the key here. Yeah. And so you go to a rather low temperature with a fast cooling rate, and then you're just holding it. So you're doing an isothermal phase transformation, and but you don't complete it. Yeah, if you just go on and on, you will get fully across the red line. You will get fully fine perlite. But it is not finished, and it stopped at the 50% of perlite. So at this point, you will have in your microstructure 50% of fine perlite and the other 50% of gamma phase, the austenite, because they didn't manage to have enough phase transformation yet. They are still there. But before they do anything, you just quench it. You quench it to a even lower temperature right here, so around 500 degrees C. And by quenching, I think you should keep in mind, by quenching, you will not have any phase transformation by diffusion. Yeah, the only phase transformation could happen by quenching, so rapid cooling, is a Martin-Side transformation, which is diffusion-less. But we're not there yet, right? This is gonna happening, and this is not gonna happen. That's why by this quenching, you're at the position still 50% of fine perlite and 50% of gamma phase. But the gamma phase now is somehow not stable anymore, right? And then you're gonna continue to do the isothermal, yeah. And as you can see, the curve is not just continuously plotted, and it is dotted to a time backwards. Yeah, we cannot go back to the time, right? That's something you can easily imagine. That's why we're using some some dots to connect here, because this is not exactly going back to the time. This is actually another way to shift those few noses to the right, because if we're going to continue with the time, but your phase composition is not exactly here, because if you just put it here or continue here, it is somehow giving you an impression our microstructure is something about, let's say, 30% of bainite and 70% of austenite, right? So this is the 0 of bainite, and this is 50% of bainite. No, actually we are having 50% of fine perlite and 50% of austenite. That's why we go back to the austenite region. Yeah, so the 50% of austenite will be just as it is purely austenite as the initial austenite. But you need to keep in mind the 50% perlite, fine perlite, will remain as it is. So you have to remember this point. And when although we converted to back here, the 50% of perlite cannot go back to austenite, yeah, because to go back to austenite, you need to increase your temperature. Yeah, that's the key point. So starting from this time, actually rather that time, your 50% of austenite will start to do the transformation. But now you need to only consider your austenite, right? You can treat your austenite as a full, as 100%, and it will start transformation. So when it reach this point, you have basically bainite transformation, 50% of bainite and 100% of bainite, and you just somewhat hold it further. Make sure you completely cover this time that you converted back. Yeah, you have to cover this time back by a certain amount, and even with a little bit of safety margin, you make sure at the end you have full transformation to bainite. But now you have to keep in mind, this bainite is only transformed from this 50% of austenite. Although the transformation is 100%, but initially you only have 50% of austenite, because the other 50 is the fine perlite. All right, now you have at this point 50% of fine perlite and 50% of bainite. You do a quenching. So the other question some of you might wondering, oh, I have my Morningside starting temperature. Yeah, you're doing quenching, I should get my Morningside. That is not true anymore, because actually the Morningside start temperature, it is of course temperature dependent only, so we just draw a horizontal line, but it is only available to FCC. Now, if you remember the Morningside transformation mechanism, it is basically converting FCC to BCC, and that is a way to just overcome the oversaturation of carbon atoms. And here you have completely very comfortable carbon atoms in perlite and austenite, and bainite. They don't need to suffering from any oversaturation. So although you're doing a quenching, but you will not have Morningside. They are perfectly in the good phase of, in a good equilibrium of bainite and fine perlite. That's why after this complicated temperature time history, finally you will get 50% of fine perlite and 50% of bainite. All right, hopefully that helps you to further explain, further understand this example. And if you just capture the core of it, I think you will be able to master a lot of similar exercises. All right, thank you guys, and see you next week.